Alright, yeah, welcome back to my channel, and I'm glad to have you here. In this video, we're going to be discussing about regulated power supply using linear regulators, and we're going to be doing that using first Zener diodes combined with BJT transistor. Then we go to the popular LM317 adjustable voltage regulators. If you have not subscribed, I want to kindly ask you to subscribe to my channel and click the notification button so that you can always get the latest videos when we post them. Alright, to do this, we're going to use an online tool called ForStart. So you go to your browser now and go to www.forstad, ForStad, FALSTAD.com. So go there. When you go there, you are going to have a web page that looks like something like this. You have something that looks like this. You definitely have a circuit running here. It may not be the same as my own circuit, but you definitely have something running on the screen. All right, have you done that? If you've done that, then let's begin. Okay, so we want to talk about linear voltage regulator. In our previous examples, if you watched it, we described how to use diode for rectification. So you can look for the video that talks about diode and rectifiers to see how to do that. So we are just going to repeat the same circuit here. First, let's set this back to full screen so you can see in full screen what we are doing. Okay, having done that, I'm going to delete all of these circuits. Let's create a blank circuit. So I have a blank circuit now. So to recreate that circuit, I need a voltage source. Let's get the voltage source, an AC voltage source. Let's use this AC voltage source, 2 terminal. That's beautiful. Then we need a transformer. A transformer is under passive components. Let's draw a transformer. I'd like to make it a custom transformer. Okay, I will edit that. Let's remove that. Draw, add custom transformer here. That's what I'm looking for. So I have this. Let's edit that transformer now. So I'll make this 220 normal supply voltage in Nigeria, or wherever you are. You can add that voltage here as a primary voltage, then the expected output voltage. So in this video, we want to make a simple 12 volts, or okay, let's do 5 volts regulated power supply. For that, we need like 7 volts transformer, there about 7-8 volts transformer. So let's just stick with 7 volts. So 220 ratio 7, and click OK. So I have this here. I'm going to connect this to this. Now to connect, I'm actually using shortcuts. I'll show you how to draw a wire now. So this is already connected. Let's edit this and set the voltage to 220 volts. Max voltage, set the 220 volts this here, and set the frequency to 50 hertz and select OK. So we've done that already now, and the next thing is to add our rectifier circuits. Let's see, there should already be a sub-circuit, a circuit that is already full rectifier circuit and filter. We can just bring in this. Of course, it has cleared what we had before, but we can easily redraw it. So I'm going to stop this simulation, delete this line, delete these points, and put in my transformer. So this is to drag or to select. You come to draw and select/drag, or you can use the shortcut space key. So in this mode now, I can drag my components or whatever I select anywhere. Alright, so I want to bring back the transformer, custom transformer. Let's do that. So let's edit it. 220/7. Let's make it 8 volts. So to draw a wire, you come to draw and you select wire, or you add wire, or you select, or you just press the key W. So I'm going to draw my wire now. And connect this point back to this point. Okay, so the source voltage is 220 volts, and the frequency is 50 Hz. Apply and OK. So having done that, let's start the simulation to see if what we have has been affected. So over here, this waveform here shows the waveform at the primary side, at this side, and over here shows the waveform at the secondary side. So you see that the primary side, the DC voltage, the AC voltage there is 220 volts, and at the secondary side you have 4.346 voltage. We have our rectifier circuit now, and we have our capacitor filtering the DC waveform. Let's change this capacitor to a polarized capacitor. Add polarized capacitor. Then I'll press W to connect it. And then let's set the value to something like 1000 and click OK. So at the output we have like 6. Then let's change this to like 1000 ohms. Okay, so you notice that the simulator here is asking for the maximum voltage. Let me quickly show you a relationship between maximum voltage and the voltage you see on your meters, which is called RMS voltage. So RMS voltage, the relationship between RMS voltage and maximum voltage is given by that value of maximum voltage divided by √2, square root of 2. So that means that my real life maximum voltage, if I were to have 220 volts RMS voltage, is given by 220 multiplied by √2. Let me quickly show you that in a formula. The maximum voltage Vmax, which is what the simulation needs, is given by your Vrms. That's the Vrms is the voltage that your meter will measure, multiplied by √2, square root of 2. So our Vrms is what we normally use. You hear things like the supply voltage is 220, it is 180, it is 200. So in all of that, you are actually referring to the RMS voltage. Do you get that? You are actually referring to the RMS voltage. So to put that in, so the simulator we are using is asking for maximum voltage. So if our Vrms is 220, the maximum voltage will be 220 multiplied by √2, and that will give us what? Let's check into the calculator. (220) multiplied by √2, 1.4142, give us 311.124. So this is the value we are going to input into our simulation, 311.124. So let's go back to our simulation now. So I'm going to input 311 here and apply and click OK. Okay, having done that, all right, so at that, okay, that's beautiful. Now you see the output voltage of this transformer entering into 7 volts, 7.1 volts, thereabouts. So we are now going to regulate this output to 5 volts. And the first method is by using a Zener diode. Now, if you've watched the video on how to use Zener diode before, you will understand this method. I will just repeat it here for repetition's sake, and so that we can understand when we want to use a transistor for the same function. So I'm going to add a resistor for the Zener diode. So I'm going to add the Zener diode now. Let's see where is Zener diode. Zener diode. Yes. I'm going to connect it. Let's set the, I need a resistor, I need one more resistor. So this resistor is serving as the load, and this one is serving as the current limiter for the Zener diode. So let's set this as 100 ohms, and 1K is still good there. Oh, sorry. Okay, so now this is a perfect waveform. What's the voltage of this Zener diode? Let's find out. Okay, so the voltage of Zener diode, the breakdown voltage is set at 5.6 volts. So let's set it to 5.1 volts and click apply. Click OK. So let's start the simulation. You will notice the voltage at the output will become 5.1 volts. You see now 5.119 volts. That is a simple linear regulator there. Howbeit, you are limited to the amount of current the diode is Zener diode can supply. So in most cases, you have Zener diode in the capacity of 1 watt. 1 watt at 5 volts will mean that you can only get 0.25 ampere out of it. If you have 2 watts, it means you can get like 0.1 ampere out of it, or I mean 0.5 ampere. But if you need more current, then that's where a transistor comes in. So let's see, how do I add a transistor to this circuit to make it supply more current to my load? So I'm going to stop the simulation now. We will still need the Zener diode, right? So, but let's remove this part first. Let's remove all this part first too. Okay, this can still be there. This can still be there. So we are going to take the output of this and connect a transistor, an NPN transistor. So let's go to draw and select active component and select bipolar NPN. So let's draw it. I want it to look like this. Okay, don't worry. We are going to have to flip it so that the emitter faces this side, the collector faces this side. So let's flip. That's X. So that's it. Oops. So the collector of the transistor directly goes to the power supply. Now we are going to apply the regulator circuit of the Zener diode to the base of the transistor, right? So I need my resistor and I need the Zener diode. So the resistor goes to the power line, connects to the Zener diode, connects to the base of the transistor, and this side goes to ground in this manner. Are you following? So this is be the output of our power supply. I'm going to remove this place, remove the scope from here. Let's add another capacitor as this output. NUF is sufficient actually. Minor, let's add this. Let's make it a polarized capacitor. Draw capacitor. And the other end goes to ground. Okay, so this is a complete regulated circuit. Now let's see the characteristics of this transistor. You have the beta to be 100. Okay, it's not bad. So we can still make this like a 100 ohm or a 470 ohms. Let's make it 470 ohms. And set the voltage now. Now, what voltage are we going to set? Are we going to set 5.1? No. The reason is this. The base to emitter of a transistor always drops 0.6 to 0.7 volts. So we need the voltage at the base of this place and the voltage at the emitter has the relationship that the voltage here, VB, is 0.7 volts lesser than the voltage here, VE. So if you want to know the voltage at the emitter, we just have to know the voltage at the base and subtract 0.7 volts from it. So let's make it practical. If the voltage at the base is 5 volts, the voltage at the emitter will be 4.3 volts thereabouts. If the voltage at the base is 10 volts, the voltage at the emitter will be 9.3 volts, around 9.3 volts. One more, if the voltage at the base is 7.7 volts, the voltage at the emitter will be what? 7 volts. So since we are trying to create a 5 volt regulated output regulated circuit, what should be the voltage at the base that we are looking for? 5.7, right? But you will not find 5.7 volts Zener diode in the market. You will find 5.6. So 5.6 is still good. So let's edit the model and change this to 5.6 volts. And apply that. And okay. So having done that, let's see what will be the output voltage here. I will just right click and select view a new scope. Okay, my oscilloscope already appeared here. So let's start simulation and let's see what we have at our output voltage. And meanwhile, understand that this simulation is not happening in real time. If you look at the time here, this is 2.467, 2.47, 2.48. So it's not happening in real time. So you have to wait. We can speed up the simulation speed from here. So it's responding faster now. So what's the voltage at the output there? Where I'm seeing 10 volts. Oh, two bad connections. Okay, there is a bad connection somewhere. Let's stop the simulation. See from here, two bad connections. Stop the simulation. This red point, I think they are the bad connections in this circuit. So I'm going to delete it and redraw it. Let me delete all of this and delete this. So we just redraw that entire point. Yeah, that's good now. I'll also delete this, and redraw that point too. Good, all connections are good now. Okay, let's add an oscilloscope to this end. View in new scope. Okay, let's start simulation. Good, everything is good now. So at the output now, look at the voltage. At the output we have 5.564 volts, right? Well, that's still fairly good compared to the voltage at this point. Let's add the scope here, view in new scope. The voltage at this point was 7.88. The voltage at the output is 5.564. Let's add the load resistor to it. To add the resistor, you come to draw, add resistor. You can just click on letter R and draw your resistor, then connect your resistor. Then add your ground. You can select your ground from here, add ground, or just press letter G on your keyboard. Then I'll connect the wire. Now once I did that, let's set the load to like 300 ohms and let's see what happens. Okay, you see the voltage dropped by 4.9 volts, 4.8 volts. So your load also affects how much of regulation you will get eventually. The higher your load, the poorer the regulation becomes with linear regulators. So you see now the voltage is around 4.9 volts. Now linear regulators are actually very ineffective. All the voltage, excess voltage. So for example, you are stepping down like 8 volts to 5 volts. So all the excess 3 volts is converted to heat. So in most cases, you have to attach an heat sink to your main active component there, which is this transformer here. So that's a kind of linear regulator. As we wrap up this video, let's call it an adjustable voltage regulation or regulator using the LM317 IC. So to do that, I'm going to delete all these regulator circuits and use a single IC to achieve what you have there, these 3 components: resistor, transistor, and capacitor. So let's just delete those ones alone. Let's just delete them. Let's delete them. Delete. Okay, that's good. Stop simulation. And let's bring in our LM317. Let's see. Okay, so this is LM317. So it's a simple circuit. I'm just going to bring it here. The input here connects to your input side. The output here goes to the output. Now, this is the adjust. What do you do with the adjust? You can use just 2 resistors to adjust how much voltage you will have at the output. Now, we will really love you to build this circuit physically, so just follow this circuit. So I will need 2 resistors, right? One resistor here. I will use 220 volts. 220 volts is good. 220 ohms, I mean, is good here. Then a potentiometer here. Let's have the potentiometer. And we have to delete this. Let's also delete this. So let's join them together now. This resistor connects to the output. This one connects here. And this one connects here. This one connects to the adjust, and this also connects to the same point. This point also connects to this point. You can do it like that. And this point connects to ground. Now, with this circuit, we have created a simple adjustable voltage supply. Let's make this 5 kilo ohms and click OK. Now, the input voltage is still from the transformer is still around 8 volts. What are we going to have on the output? Let's start simulation. Now on the output, let's stop this simulation, remove scope. Let's first add the scope here to see the inputs. Then add another scope here to see the output. Okay, that's beautiful. So the input is 7.997 volts, the output is 5.857 volts. If we adjust the value of this resistance, right? If we adjust the value of this resistance, the output voltage is also going to be adjusted in the same manner. So let's see that. You see the voltage dropping as I adjust downward the potentiometer. Let's bring it all the way downwards. See downwards. You have 5.1 volts, and it will stay like that. If we bring it still downwards, you can have lesser voltage up to 1.2 volts. You just have to wait for the simulation. You see now, this is my voltage, this is the current voltage here, 1.44 volts. 1.44 volts. If you begin to increase back, at this point you see 4.9, 5.0, 4.84, 4.81, thereabouts. So let's do this. Let's make the transformer to be like something like a 15 volt transformer and click OK. So let's start the simulation. Okay. The voltage is rising, but it's not in real time. Let's just chill out for it till it gets to its maximum voltage. Okay, if you see, you discover that the voltage at the output is now a flat 4.967 volts. Even though the voltage at the input is still going on, it's still increasing. Presently, if we were to be in real time, this is 5.4 seconds gone. So let's assume, let's begin to adjust the value of this resistance here. You see, as I adjust it upward, the voltage is also increasing and it remains steady there, right? So this is simple voltage regulator circuit. I'd love you to build yours. You need a transformer, 220 volt to 15 volt transformer. You need 4 diodes. You need a capacitor, 470 microfarad at 25 volt or 35 volt is good. You need your LM317. Then you need 220 ohm resistor. and a 5 kilo ohm potentiometer or 10 kilo ohms. Then you need a 10 microfarad capacitor, and this load part optional, but you should add it. Alright, so that's a simple regulator circuit. Wow. That's a simple voltage regulator circuit using the LM317 voltage regulator IC. You can practice this in your own simulation. Don't forget the app is FALSTAD, FALSTAD.com. So if you go there, you'll be able to do your own simulation, or you can just go ahead and build these same circuits and let me know what you think about it, what you feel about it. In the next video, we are going to explain DC to DC converters and how they work, and how it surpasses in efficiency linear regulators like LM317 and transistor and Zener diode based regulators. Thank you for watching. Please do not forget to subscribe to this channel and click on the notification button so that you can always receive the latest video when we publish them. Thank you. Bye.